Hello everyone, welcome to this lecture of the course Digital Electronics and Circuits, and in this particular lecture we will be talking about universal gates. As you might be recalling, right, we have already spoken about basic gates in one of our previous lectures where we talked about AND gate, NOR gate and NOT gate, right? AND gate, OR gate, NOT gate, and we discussed the truth tables for these three gates, and we also spoke about three input AND gate. In this particular lecture, right, we will be talking about universal gates, and NOR and NAND are called universal gates. So I will tell you what does this mean, that what is the meaning of a universal gates. But just to give you a brief background, right, we already spoke about AND gate where we said it's a two input AND gate. Then we discussed three input AND gate also, A, B, D, let's assume like this. We spoke about two input OR gate, and we spoke about NOT gate also, right? And I briefly touched upon NAND gate and NOR gate also in one of the lectures where I said NAND gate is nothing but NOT of output of AND is NAND. Similarly, NOR is nothing but NOT of output of OR gate. This is NOR gate. This is NAND. This is NOR. Okay. So just to tell you the basic, right? AND gate, OR gate, and NOT gate. These three are called basic gates, and that's because we can realize any Boolean expression or any Boolean circuit by using a combination or mixture of these three gates. Correct? But NOR and NAND gates have a property that any one of them can create any logic Boolean expression if appropriately designed and used. This means that we can create any logical Boolean expression only using NAND gate and or only using NOR gate. Right, we don't need any other logical gates for this. So if we play around NAND gates, we can realize any circuit only using combination of NAND gate. Similarly for NOR gate, and that's why these gates are called universal gates. Is this clear? Basic gates and universal gates, NAND and NOR being the universal gates because any one of these could be used to realize any Boolean expression. Let's look at it in further, right? We will look at few of the circuits further. Let's look at NAND gate first, right? I simply told you that NAND gate is something like this. Oops, this became a bit bigger. Let us remove the. Okay, so let's look at a generic NAND gate. We have A, B, and C. Let's create a truth table for this NAND gate. We have A input, B input, and C as output. 0, 0. All the possible combinations with A and B are 4 combination 2 raised to power 4. And of A and B is 0, so not of that would be 1. Similarly 1, 1, and 0. So this is a truth table for a NAND gate. Now, as I said, like we can realize any Boolean expression using this universal gate, right? So let's start with the basic thing. Let's try to realize all the basic gates using this universal gates. Okay. Let's begin by NOT gate. What is NOT gate? Output in NOT gate is tilde of input. So basically this means C is equal to NOT of A. So basically, and NOT gate has only one input. Now, if I have to realize a NOT gate, what should I need? I need an input A and I need to have a NOT of that, correct? So this is as good as saying NOT of A dot A, right? A could be written as A dot A. We already saw one of the Boolean laws, correct? Now, if I do AND of A and not it, that becomes a NOT gate. So basically, this simply means if I have an input A, I supply that input to both the inputs of NAND gate, I will get an output C, where C would be equal to NOT of A and A, which is equal to not of A. So this will be our NOT gate, and we have realized a NOT gate using an NAND gate. Correct? Going forward, right? If we look at something like a OR gate, what is the truth table of a OR gate? In OR gate, we have C is equal to A or B, right? Where we say if we have A, B, and C, we have a truth table like 0001, 1011. This is 0111. Here, what we can say, C is also equal to, right? Basically, I could say C is equal to A bar dot B bar is equal to C bar. Because if I take note of this, my C complement here would be 1000. My C bar is equal to A bar into B bar, which implies my C is equal to A bar dot B bar whole bar. This is nothing but expression of a NAND gate, right? So if I have to realize a OR gate using a NAND gate, what I can simply do is I can take an input A, I can supply it to a, I have to NOT it first, right? NOT of A is something which I can realize using an AND gate, which you have already seen. So this is A, this will become A bar. Similarly, we have B, this will become B bar. And then we have A bar dot B bar whole bar. This we will supply to one more NAND gate, and this becomes A bar dot B bar whole bar. This is nothing but OR gate as a function of NAND gates. Correct? Now similarly, if we have to realize an AND gate using a NAND gate, that would be pretty simple because my normal AND operation is nothing but C is equal to A dot B, right? And what my C bar would be? C bar would be A dot B whole bar. So what I can do is I can have two back-to-back NAND gates to realize this A and B operation. So basically what I say is if I have an A, I have a B. What I can simply do is this would be nothing but A dot B whole bar. And now what we do is we do a complement of this. Complement of this is nothing but a NOT gate, and we have already seen how to realize a NOT gate using a NOR gate. We can simply split it, supply both the inputs of an AND gate using this A dot B whole bar. And since this is a NOT gate, it will be A dot B bar whole bar, which will be nothing but A dot B. So this is realizing AND gate using an AND gate. Correct. So we looked at a NAND gate. We saw that okay, this is a NAND gate, and we realized three basic things from that. We derived NOT gate using that NAND gate where we split input in, like where we supply the same input to both the inputs of an AND gate, and we said okay, we will obtain something like C is equal to A bar. Then we said like okay, OR gate can also be obtained using a NAND gate. Similarly, AND gate could also be obtained using a NAND gate. Basically, and then we said like all the basic gates are AND gate, NOT gate, and OR gate, which means that any Boolean expression could be realized using all three of these gates. And what we have done is we have made these gates from NAND gate itself. So that would give us indication that these particular gates could be obtained. All the Boolean expression could be solved using NAND gate itself. Thank you.